Hello there, everybody, and welcome. This is Professor Thayer with you here today to talk to you about bonding. So now that we have gone through and talked about solving particle in a box, and we've seen a little bit about how quantum mechanics can be used to give us some insights into how the electron density can be obtained, the next thing that we want to do is we want to move towards looking at the molecules themselves. How do molecules actually form? How is it that we form that atomic bond between two atoms? So we're going to explore that today. Now, usually I'm lecturing using the notebook, and I'm writing some notes for you. But today I decided to do the slides instead because the bonding is nicely enhanced by some real pictures of molecules and the density pictures and so on, which are a little bit difficult to draw accurately. So we're going to go ahead and have a slideshow for you today instead of our usual format. So let me go ahead and share my screen with you. And let's go ahead and get started. I hope I have my PowerPoint. Here we go. And let's start this. All right, so we have now seen the Schrödinger equation, the wave equation, and we have seen H psi equals E psi, and we have even seen how we can actually go ahead and solve this for some simple systems. And also we have this idea that the Schrödinger equation can be written for something more complicated than particle in a box. We can do rigid rotator, we can do the hydrogen atom, and there are also some other models as well that we could do, and they all follow us kind of a similar format here, where we're going to convert this into the into individual equations that we can solve using the method of the second order linear homogeneous differential equations, which we talked about a few weeks ago. And so the H psi equals E psi then basically boils down to doing that differential equation solution. But this is also an operator problem because that H, which stands for the Hamiltonian, is in fact an operator. And then it's also an eigenvalue problem because we see that H psi equals E psi. We cannot just divide out by psi on both sides of the equation. That's not quite how this works, because this means something different than multiplication, right? So the psi is the eigenvalue, the thing that's on both sides of the equation. So we've seen how all of these things actually can be solved. And the reason why we solved this is because we're interested in getting out a couple of pieces of information. E is the energy levels, and we've seen that that gives us some insight into how we can get out those energy levels that had been observed from the spectroscopy in the early days. And that has brought to conclusion that disparate thing about classical mechanics, right? We wondered, how come you look at light given off from some like fluorescent lights and it comes out in bands, right? And we talked about this in the first lecture where we were wondering, like, well, why does that happen? And so now we have the solution, and that is because the electrons are jumping between the energy levels, which the Rydberg equation helped us to understand, but they didn't really know why that was the solution. But then we saw that in the solution of the particle in a box equation, when we have the the bound ends and you have the electrons going around a bound circle, that the quantization drops out of this because falls out of this as a solution, because we have a solution that involves this sign, right? A sign of x equals 0. And when does that happen? Well, it happens anytime when the sign equation is equal to 0, which is going to be periodic. So it'll be at pi, but it will also be at not just 1 pi, but 2 pi, 3 pi, and so on. And so this is where our quantization came from, which is what gave us those that quantization, which then gives us the energy levels. So the energy levels are also quantized, which we saw from the particle in a box example. The other thing that we want to get out is the psi itself. So the psi itself is actually the wave function, as we know. And the wave function is going to be very important because it provides us with information to work out the energy levels, but also provides us information that can be used to actually get the probability density of where the electrons are, that is the electron clouds. So we kind of just, draw some shapes. And in Gen Chem, we might just draw some circles around the nucleus and label them 1, 2, and 3, which is fine. And a little more sophisticated, we can draw the SPD and F orbitals. But where does all of that come from? Those are some of the things we're going to talk about, the origins of that today. But it comes from solving this equation. So the solution to the Schrodinger equation gives rise to the quantum numbers, and essentially those quantum numbers mainly come from the separation variables, because when we just solved the classic wave equation, we didn't really have quantum numbers, but we have these arising from the separation of the variables that's needed in order to solve the second order linear homogeneous equation, because we can't solve multiple of these all at once, so we break it down into parts. But when we assume that separability, we do get that separation constant, and that is then going to give rise to the quantum numbers. So the location of the electron is a probability. You never can know exactly where the electron is. Well, why not? Remember, we talked about the Heisenberg uncertainty principle. So Heisenberg said you can't actually go in there and measure it because, well, the beams to see it is requires a very high energy, right? So small wavelength, high energy, and you go in. But the problem is that when your beam hits the electron to actually detect that it's there, it's going to kick your electron into a new place, right? And so you can't ever really know with 100% certainty. But we do the best we can, and we learn this information from the psi star psi, or the effectively the square of that wave function. So when we actually draw our orbitals, we don't in fact actually know where the electrons are. What we're actually doing is we're saying where we think the probability that they're going to be is most probable. So the density actually comes out. So this, for example, is like a 1s orbital, which is basically a sphere. Excuse me. So here's the sphere, and so the idea is the electron, well, really the electron could be anywhere in the whole universe, but the likelihood of it being within a certain place is illustrated by the shading here. And so what we do is we draw an annular ring to indicate the cutoff for 90% of the electron density and call it good, and say that's the orbital of where it's at. And so if we were to zoom out, like we could, so this is the same scale, the cutoffs could be at different locations. This is how you get your radial probability. So here you are getting some information about, well, if I were this far out, how much density would I encompass, and so on, as you make these various rings. So you could, of course, make these rings get smaller and smaller so that they're tighter together, and add more rings here to get a higher degree of accuracy. And then we could plot the radial probability. So this will be the distance from the nucleus, and this will be the likelihood that the electron would be found at that place. So what we see is that it can't be at the nucleus, but there'll be a place near to the nucleus where it's most dense, and then as we come away from it, it's going to be less and less dense because the probability is getting smaller and smaller. So that's just for one orbital, but in fact, we might have multiple orbitals. So when we take a look at this, we need to consider the fact that there are 1s, 2s, and 3s orbitals going around. And so these, in fact, are inside of each other, right? So the 1s is smaller than the 2s, and the 3s is the largest of these three. And so each of these exists and have their own density profiles. But as we are drawing these, we can see that they're in fact actually nested inside of each other, and they could have some nodes of density in them, as is being shown here. But when you look at it as the spherical shape, you don't necessarily see that. So the density is a complicated thing. So this gives us an idea of the radial distribution of other orbitals. So here we have the SP and D at the shell level of 3. So you'll see that it's it's complicated, and we call this the penetration because we see that the 3s has some density very close to the nucleus and then a little further out, and then we have the P density, right? Okay, and the D density. So they have some different kinds of shapes that are going to be distance dependent from the nucleus. So the different radial distributions are going to come from the different energies. They're going to be more closer density. It will have a more stable energy. So we can draw an energy diagram as is being shown over here. So the 1s is the most stable, and then the 2s is a little bit further out, and the energy is higher. The 2p is then going to be a little bit higher than this. And then when we get to 3, we're going to have the SP and D orbitals available. So you see we have these different ones, and we have these higher energies available to it than for the lower ones. The principal quantum number is n, the one we have just solved for using quantum mechanics, and we saw how that arose from the particle in the box, from the periodicity and the sign solution. That is the solution when you have the complex roots from the the second order linear homogeneous differential equations. So if we have these various shells, we're going to see that we're going to have these different energies available to them, and n is essentially indicating which shell an electron is at. So let's see how we actually got in from the particle in a box, and was introduced in the particle in a box problem after the boundary conditions had been applied. Remember that we needed those. In the generic solution, we did not have all of the information because you need to know what the integration constants are going to be. So the periodic values of 0 within the sign function implied the periodic conditions at an interval of n. So remember, we had, here's the boundary conditions, right? So psi of 0 equals 0 was one of the boundaries that we had, and this implies that b is going to be equal to 0. So psi of x equals a sine kx, right? So then we solved this, and this is how we got n. Then we also have that the psi of L equals 0. This is the wave function, must also vanish at the distance L, right? So we have the wave bound at two sides. Oops. Bound at two sides, at 0, and at the L, the length of the box. And so it will vanish at both of those. In other words, it's fixed. And this gives a sine KL of 0. And so for non-trivial solutions of A, we had that KL equals n pi, where n is going to be 1, 2, 3, and so on. So this is your quantization. And so K then was equal to n pi over the length of the box. So this is also led to the quantization of the energy. It's the principal quantum number and tells the shell number. All the quantum numbers are related to n. So what about transferability to other systems? So you can connect to other quantum systems. So the principal quantum number n similarly arises in the hydrogen atom solution, just like it did in particle in a box, and other quantum systems when solving the Schrödinger equation with their appropriate boundary conditions for those different equation types. So in the hydrogen atom, n will determine not just the energy level, but also the radial distribution of the electron. The second quantum number is L, and this is the angular momentum. This will tell us the shape of the orbital. So you might have learned from Gen Chem that it's SP, D, and F, and the shapes are the sphere, the dumbbell, the donut shape. I like to call it the donut ETC, and fireworks shapes, which are depicted here to the right. And so we see that some of these shapes are kind of interesting. And these are things that we've kind of just gave you in Gen Chem and expected you to sort of just accept that. But here we can actually dig a little deeper, because now we know that the solution actually has to do with solving that linear homogeneous differential equation, and we get out psi, which is the probability density. So these are representative of the probability densities of where the electron can be when it's in these different orbitals. So the angular momentum will tell us the shape of that orbital. So L can run from 0 up to n minus 1. So if n is 1, what is n minus 1? It's 0. So the only n minus 1, if n is 1, n minus 1 is 0. So the only allowable answer is 0 for that. And when n is 2, it can be 0 or 1. So you see it's basically going to run starting at 0 up to just one integer lower than the orbital number. And of course, it's going to be positive. Okay, and for n is 3, it's going to run from 0, 1, or 2 to get our quantum number. Where did L come from? It arises from solving the Schrödinger equation. So the Schrödinger equation for the hydrogen atom is not something we solve by hand, but is something that you can understand what's going on here. So the Schrödinger equation has, just like we had before, some kind of a Hamiltonian, right? Some equation about how things are going to be moving. A major difference is that this one is going to be in terms of R, theta, and phi for the hydrogen atom. So mu is the reduced mass of the electron nuclear system, which is this right here. V of R equals Z squared over 4 pi E0 R. This is the Coulombic potential. Oh, sorry, with a negative in front. So V of R is radially dependent because we have this R for the distance in there. So that is the other term. And del squared, this is the Laplacian and spherical coordinates. So what is del squared? Well, it's kind of like a double gradient. It's like a multi-dimensional gradient term, which is telling us about the slope. So let's solve the Schrödinger equation. So in the spherical coordinates, the wave function is going to be phi of r theta and of psi of r theta and phi, which can be separated out into 3 different parts. So this is basically an assumption, right? This is the similar thing to when we had the distance and the time. And we decided to separate those out into 2 different parts back in the classical equation. So here we're going to play a similar game where we assume that these are separable, and then we do it, and then post priori we can demonstrate that that was an okay thing to do because we can't have any cross terms. And so long as they all separate out, then separation of variables is okay. And then we can get our separation constant. But this one, as we see, has 3 variables. So we're going to have the radial component, which is R of R, which is the dependence on the radius. And then we're also going to have the angular part, which is theta and phi, which is going to tell us about the angular part of this as it goes around. So it's useful to express this in the polar coordinates, which is where these are going to come from. So substituting this into the Schrödinger equation and separating the variables leads to 3 coupled differential equations, one for each of the coordinates, r, theta, and phi. So the procedure for doing this is really quite similar to the separation of variables that we had done before. So because we're working in polar coordinates, it has a radius and 2 angles, the theta and phi, and we separate out the radial part of the angular part, similar to separating out the periodic boundary position into the positional and temporal parts. Here's what the radial solution looks like. So we're going to have the separation of variables and the quantum numbers. So, and this also gives us a bit of that connection to the end. So the radial part of the Schrödinger equation is going to lead to this, these equations here. So we have information about the radial part, right? So here we have our dependence on R. And now we have this part over here, which is, all right, got a Coulombic term, got an energy term, and some constants out here. So here the L times the L plus 1 appears as a separation constant from solving the angular part of the equation. This is where the azimuthal quantum number L first emerges. So it happened because we needed to do the separation of the variables. They've obviously done some simplification in algebra here that's a little bit more complicated than what we encountered in particle in a box, but the idea is pretty simple. So here the L is L times L plus 1 appears as a separation constant. This is where the azimuthal emerges and the radial solution imposes quantization of the energy levels. Well, why is that? It's the same reason it happened in particle in a box. So you're also going to have a very similar equation for the quantization of the energy levels in this system as well. And here is the equation that we get out from this particular system. A little bit different than the one we saw before, but hopefully you can recognize this as being pretty close. So the principal quantum number n is related to the radial quantum number n sub r and L by n equals n r plus L plus 1. The relationship shows that L, the angular momentum quantum number, is constrained by n, which is what we had said before for a more empirical reason. We said, well, once you know what n is, L is going to be related to it. Well, this is mathematically why that arises. So for a given n, L can take on the values from 0 up to n minus 1, just as we had said based on empirical observation earlier. But that's only half of the, well, a third of the equation, because we have the hydrogen atom being a function of r, theta, and phi. So now we need to talk about the angular solution. So that was the radial solution, the part that pertains to the radius. But what about the theta and phi? That's the angular part. So the angular part is related to L because the angular part of the wave function involving theta and phi is going to lead to the spherical harmonics. Y of L ml of theta and phi equals this theta and phi, these theta and phi equations. Kind of looks a little bit familiar. It kind of looks like we've just done separation of variables again. So the azimuthal quantum number L determines the shape of the orbital and the possible values of m sub L, which range from negative L to positive L. So how does L emerge? Mathematically, L arises from the separation constant when we solve the angular part of the Schrödinger equation in the spherical coordinates. Physically, the L is related to the orbital angular momentum and the shape of the electron cloud. So its relation to n then is that for a given n, L can range from 0 to n minus 1, reflecting the hierarchical structure of the energy levels and the orbital shapes. So the connection between L and n comes from the radial quantization condition. The principal quantum number n reflects the total number of radial and angular nodes, and the azimuthal quantum number L specifies the number of angular nodes, while the radial quantum number specifies the number of radial nodes. This means that L will always be less than n. The third quantum number is m, or m sub L. This is the magnetic quantum number, and it tells the orientation of the orbital. So we may have seen like px, py, and pz. We have those p lobes that looks sort of like balloons on their side, kind of a thing. Some depictions down here, some more circular shaped ones. So for a given value of L, m sub L runs from negative L up to including 0 up to positive L in integer values. So if L is equal to 0, that's an s orbital, m sub L will also be equal to 0. So that's because we have the infinite symmetry of the sphere. There's only one orientation, but p orbitals, on the other hand, have 3 orientations. So we see that they could lie along the x, the y, or the z-axis. So that cannot be an S, right? S has infinite symmetry. So these are going to be the p's. So where does the azimuthal quantum number come from? So solving the Schrödinger equation for H also requires separation of variables of the two angular parts of the equation to obtain a second order homogeneous linear equation. So we'll apply that same trick one more time. The separation of these is with the other separation variables is going to create a new separation variable. So in other words, when you solve this thing, you can have more than one separation variable. And this is just one example of that. So when solving the time-independent Schrödinger equation for the hydrogen atom, the wave function of psi of r, theta, and phi is going to be expressed in the spherical coordinates, which we are expressing just right here. So substituting this into the Schrödinger equation and separating the variables can lead to three coupled differential equations. We would have the radial equation, the polar or angular equation, and the azimuthal equation. The magnetic quantum number ML emerges from that azimuthal equation. So suppose we want to solve the Schrödinger equation for the for H and in terms of the azimuthal. So the azimuthal equation is phi dependent. So the azimuthal part of the wave function phi describes how the wave function varies around the z-axis. From the separation of variables, the phi-dependent equation will then be, oh, look at that, second order linear homogeneous differential equation, right? So you have your differentiation right here, and you have your other term over here. So this is a standard differential equation for periodic functions, and the general solution is phi of a e to the I m sub l phi. And so we recognize this from some of our previous work where we have looked at how to solve these things. A is going to be a normalization constant, and m sub l is the separation constant for these. The quantization of m sub l. So the boundary condition of phi is that the wave function must be single valued. You cannot have multiple values. So we can apply this condition. So if you have e to the ml phi, it's going to be equal to I ml phi plus 2 pi. So remember that we had Euler's interchange between the exponential and the trig forms. So we could now make that application here. So these are the values of m sub l that are allowed. And then we could use the integer, and it's going to be constrained by the azimuthal quantum number L to give these following values. So what is the physical meaning of m sub l? This tells us the orientation of the orbital. The magnetic quantum number m sub l will determine the orientation of the orbital in space relative to some external magnetic field. The angular momentum component m sub l will specify the z component of the orbital angular momentum. So we have L sub z equals m sub l h bar. So while the total angular momentum is going to be given by this expression here, the square root of L times L plus 1 quantity times h bar, the z component is going to be quantized and depend on m sub l. This brings us to the Zeeman effect, and also this ties into why the m sub l is called the magnetic quantum number. So the name magnetic quantum number comes from its role in determining the splitting of energy levels in the presence of an external magnetic field, which is known as the Zeeman effect. When a magnetic field is applied, the different orientations corresponding to the m sub l's lead to slightly different energies due to their interaction between the field and the magnetic moment of the electron. So m, in other words, is going to arise mathematically as a separation constant when solving the phi-dependent part of the Schrödinger equation in the spherical coordinates. Physically, it determines the orientation of the orbital and the z component of the angular momentum. The quantization tells us that m sub l takes integer values ranging from negative L to positive L, providing 2L plus 1 possible orientations for a given orbital. The fourth quantum number is m sub s for spin. The magnetic spin will be either clockwise or counterclockwise. So m sub s gets values of positive 1/2 or negative 1/2. This here is why we represent the electrons with an up arrow and a down arrow, indicating their spins are not the same. So the Aufbau principle says that electrons in the same orbital have opposite spins. So we've seen that that's true in the s orbital, but it also is true in the p orbital. But you might say, but that holds 6 electrons. How is this possible? Well, it's because of the individual suborbitals that are inside of it. Each one holds only 2 electrons, and they should have the opposite spin. So we see that m sub s is positive 1/2 in this case, and m sub s is negative 1/2 is the situation in this one over here. So the spin quantum number S arises from the intrinsic property of electrons called spin, which is independent of the electron's orbital motion around the nucleus. So unlike NL and M sub L, which emerged from solving the Schrödinger equation for hydrogen-like atoms, right, particularly from the separation variables, S comes from the quantum mechanics behind the Schrödinger equation, specifically from the Dirac equation and the concept of relativistic quantum mechanics. So this tells us the Dirac equation for 2 particles in the system. So the Dirac equation in the presence of an electromagnetic field. So for hydrogen-like atom, the Dirac equation includes the electromagnetic interaction between the electrons and the nucleus. So I h bar mu over times du minus mc, all of that times phi equals 0. So du is really representative of this operator here. It's taking some partial derivatives. So we have, it's the covariance of the derivative incorporating the electromagnetic vector potential, which is A sub u, mu. The nucleus can also provide a Coulombic potential. So here we have AC sub 0 equals negative ZE over R. So solving this equation gives the relativistic wave functions and energy levels of the electron and the Coulomb potential of the nucleus. The spin-orbit coupling will emerge naturally. So when the Dirac equation is solved for the hydrogen atom, it predicts not only the energy levels, but also that finer structure of the energy levels, which will include the relativistic corrections to the kinetic energy and spin-orbit coupling. So solving the Dirac equation is a pretty serious business and does require some level of math prowess beyond what we are going to cover in this class. This gives you a sense of what that content is like. So the spin-orbit coupling is an interaction between the electron spin and its orbital motion in the Coulomb field. The spin-orbit coupling results from the relativistic coupling of the electron's magnetic moment due to its spin with the magnetic field generated by the moving electron in the electric field of the nucleus. So the quantum numbers in the Dirac solution for hydrogen, the wave functions are going to be labeled by the principal quantum number n, which is from the Schrödinger solution, and the total angular momentum J, where J is equal to L plus S, where L is the orbital angular momentum and S equals 1/2 is the spin. Magnetic quantum number mj is going to be the projection along of J along the z-axis. So the presence of J reflects the coupling between the spin and the orbital angular momentum, showing how the spin is inherently tied to the relativistic nature of the electron. What are the key differences? The key differences from the Schrödinger equation for this version is the non-relativistic Schrödinger equation. So the spin is added ad hoc as a separate quantum number. In the Dirac equation, spin naturally emerges as part of the relativistic framework. The fine structure of hydrogen, including the splitting of s orbitals, that is L equals 0 due to spin-spin coupling, is going to be predicted directly from this method. So let's see about the fine structure of hydrogen. So the Dirac equation is going to explain the fine structure of hydrogen's energy levels. So prior to this, we worked with some equations that were really rather simple, but these are some more serious equations that could be used instead. Notice that we have some of the information about the quantum numbers in here. So alpha is the first fine structure constant, just right here. And then this formula includes relativistic corrections and also the spin orbit coupling. So the Dirac equation explains the fine structure of hydrogen's energy levels. So here we have E of n comma j equals mc squared alpha squared over 2n squared times the quantity in the brackets. So we have 1 plus alpha squared over n squared, and we have n over j plus 1/2 minus 3/4. So for alpha is going to be the fine structure constant. This formula includes the relativistic corrections and the spin orbit coupling is another term that's in it. So the Dirac equation predicts the existence of spin as an intrinsic property of the electronic system for our four-component wave function. The spin orbit coupling and the fine structure of hydrogen naturally emerge from the relativistic interactions. This will eliminate the need to introduce spin artificially, as it is inherently part of the relativistic quantum framework. This is just a little table that shows what the possible values are going to be for the various quantum numbers. So if we take a look at this, we have the NL and M sub L. So N, of course, is just telling us the shell, right? So we have 1, 2, and 3, and then it could also possibly be a fourth one. So L is 0, right? So when N is 1, L is 0. When N is 2, L is also 0 and sometimes 1. So right, you see it's got multiple classification systems under it. So when we are working with even more here, so here we're running from -2, -1, 0, 1, 2, we could apply this and we would see that this gives us more choices. So this tells us the number of orbitals that needs to be involved, and the atomic designations are shown over here on the right. So we have the 1s and 2s, which are familiar, and then we have the 2px, y, and z. So these are the x, y, and z oriented lobes of the axis, arranged because of the repulsion of them. Then we have the 3s, which has only the quantum number n, right? The others don't really apply. And then we have 3x, 3px, 3py, and 3pz, right, as some of the different possible orientations. So these are all the same. And then we have the considerations from over here, which these going to work with these kinds of constants here. Next, we have the s orbitals. L equals 0, M sub L equals 0. So we see we can run from the 1s to the 2s to the 3s. So we have one orientation with 2 electrons each. That would be 2 electrons total per, and then you need to see how many shells you in fact actually have. So p orbitals have L equals 1. So that means that M sub L is going to run from -1, 0, and 1. These are the 3 orientations with 2 electrons each for a total of 6 electrons. This is why P has 6 electrons in it. So here we have the X version, the Y version, and this is the Z version. So we also have d orbitals. So that's L equals 2. So M sub L equals -2, -1, 0, 1, or 2. This gives us 5 orientations of 2 electrons each for a total of 10 electrons going into the d subshells. So this is the shape of the various orbitals in D. So these are the exhaustive list of the combinations. And so what we can see is that they're wide and varied. So it looks like the most decent one, easiest to get around, but in fact, electrons may choose a different choice of the orbits. The f orbitals are going to be from L equals 3. Now, this is going to give us a whole slew of different orientations. We're going to have -3, -2, -1, 0, 1, 2, 3. So that's 3, 6, 7 different orientations. And these are the 7 different shapes of the orbitals that we can ascertain. So some of them look kind of like fireworks, and then we also have these mushroom looking things. So this gives us a total of 14 electrons. The Pauli exclusion principle tells us that no 2 electrons in an atom can have the same 4 quantum numbers. So that means that that would be impossible, and that if such an overlap occurred, that electron, excuse me, would be eliminated. So each seat is uniquely identified, just like you would have, say, like a ticket for a stadium, you would go to a very specific seat. So that would be the orderly way of doing things. But if an electron doesn't have that ordering, then the system is going to eject the electron. So each seat can hold only one individual at a time. This is showing the energy. So the energy increases on the left-hand axis right here as we go up. And then we can take these energy levels and we can go ahead and draw them out. And then we could fill them in. So this is the electron diagram. So we would fill from the lowest energy to the highest. So what we do is we write down the 1s and we put a line here. So this indicates like an available place. And then what we're going to do is we're going to fill them. So the way that the filling works is we are going to follow Hund's rule. You're going to fill each subshell before doubling up. So for example, in the 1s, you would, that's the subshell. So you would fill this 1s, so you would do up and down, and then you wouldn't put any more in there because it's full. Now, the next thing we could consider is the 2s. So this is the up and the down. There's 2 different ones, and we have some position available here. Now the 2px, y, and z, so here your x, y, and z orientations are going to allow for some more space. Now, which atom is this actually? We have 1, 2, 3, 4, 5, 6, 7. I do believe this is a nitrogen. So in the 2, as we're filling the upper electrons, what we're going to do is we first put 1 per position, right? So you go and spread it out so that each one has its own place. And then if we had more electrons, we'd then double it up after. But the idea is we're going to put them in their place as singles in the beginning, and then we would add the second one later. The reason is because adding the second one on is going to increase the energy some small amount, so it will go to the lower energy state. Here are some examples of how the electron filling is done. So if you have 1 electron, it goes here. Now, if you have 2 electrons, you'll do both in this one because you have already filled, you have a hot-filled subshell and you need to add 1 more electron. So you add it here because otherwise you'd need to jump all the way up to this one, which you're not going to do. All right, so, but if you have 3 electrons, you see you'll do these 2 first and then go here. So in other words, as we're adding electrons, this diagram illustrates how they're going to fill. So here we have 1, 2, 3, 4 electrons. So now the subshells are completely full. So the next thing we're going to do is we're then going to fill the electrons out in this part of the system in the 2p. So we would say, okay, the next electron we're going to add is going to be in the 2p. So we put it there. If you have a second electron beyond this bottom, that will also go here. And the third one will go here. And then we scaled it up a bit, right? So instead of jumping by 1, this is showing that then we would jump by 3 to fill that up. Okay, and then we can accelerate this into the higher level. So next we would take a look at the S of the next. This is the next shell out. So it would be 3s would be the next thing we would fill, and we'd do both of those. And then we would complete these P or subshells. So these are going to also all take the arrows. So this is showing a whole bunch of new ones being added on, right? Okay, and then we can also do it all the way up to the completed system, which is going to be this one right here, where all of the electrons are filling each of the positions that are available to them. This tells us the order of the orbitals filling in a multi-electron atom. So this is a really handy chart to make. Now, the way that this works is that you start at the top and going across in the straight rows across, you're going to write all of the orbitals that are available at that level in that shell. So we have 1s, 2s, 2p, 3s, p, d. So you just line those up. 4 has s, p, d, and f. 5 has s, p, d, and f. 6, in principle, could have those, but we don't actually have atoms that go out that far. So you just have s, p, d, and then 7 is s and p. So this is how you write this out. And then to actually read it off to get your filling level, you're going to go on the diagonal. So here you do your first one to get 1s, and that's your lowest energy. Then the next pass through goes through the 2s, and then you go through it from upper right to lower left by tracing out along this line. So the next one would be 2p, which is this one being written here, and 3s. So it'll be 1s, 2s, 3s, 2p. So let's see, 3s, 3p. So it should follow along here. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. So you'd also finish that off with 4f, 5d, 6p, 7s, 5f, 6d, 7p. But you see that by going along those diagonals, you correctly generate the sequence and the order of their energies. So let's talk about how this relates to the periodic table. Now, the periodic table was something that we had mentioned in our introductory chapter, had been empirically worked out, but nobody knew exactly why the periodic table had the properties that it did and why the elements lined up the way that they did. Now, the reason why has to do with quantum mechanics. It has to do with the filling diagram. So notice that we have, okay, this is your 1s. So as you add more electrons on, as we move through the periodic table, this is hydrogen here. This has only one electron, and this is helium. It has 2 electrons. Both of these are filling the s subshell. So these go like so. And now here is the row 2. So this is going to be filling of the second shell. So we'll fill the 2s. Now s, recall, does not have any d's. 2s has so 2 has s's and it has p's. So we have, here are the s's and here are the p's. Now, how many electron slots do we have in the p's? Well, we have X, Y, and Z, and they each hold 2. That's 6. So this is why this section of the periodic table is 6 wide. And so this also is similar to the 3s or the 3. So we have 3s and then the 3p's. So this is why the periodic table is arranged in this way. Now, once we get to the 4s, we have the 3d's. Okay, so the 3d's are coming down under here. But remember, we have that order of the filling: 1s, 2s, 2p, 3s, 3p, 4s, 3d. Right, so these are your 3d10s right here, and so there should be 10 slots right here, and in fact there are, and that comes from the 5 orientations that we have available, which each can hold 2 electrons. So you have your 3d10, then you have your 4p's, and now we go to the 5 s's, which is going to take 2. And so you'll see then the pattern here that as we trace out these patterns, that it matches up to the periodic table, right? So this has then the F subshells getting filled. This is for the lanthanide and actinide series down here, which are going to then be filling those F orbitals, which are going to be highly complex. We can also write the electron configuration. This is how the electrons are distributed among the various atomic orbitals in an atom. So what we would do is we would write the principal quantum number n, then we will write the angular momentum quantum number, which is going to be L, and then this is going to arise from the number of electrons in the orbital or the subshell. So you have 1s1, 1s2, and so on. So you would just be writing it just like it's been shown here. So this is 1s1, 1s2, then you have your 2s1, your 2s2, your 2p1, 2p2, and so on, to fill out these diagrams. So these basically you just follow as you're filling your periodic table. So you have a particular element, you just simply find where it is on the periodic table. It always contains the ones that are below it. So meaning below being, well, actually higher on the periodic table, because the periodic table goes from top to bottom. And also it will contain the electrons from the lower shells and any lower orbitals from where it is, which means higher on the periodic table, but closer to the nucleus in the electron system itself. And that's how we get this. And then we have the corresponding orbital diagram. So for example, 1s1 has one electron in it. So we have one box with one arrow in it. This also gives rise to the paramagnetic versus the diamagnetic systems. And this has to do with some properties you can actually measure with magnets. So in the paramagnetic situation, you can put some magnets nearby. And in paramagnetic, you have unpaired electrons. So this will be highly magnetic. So this is what allows certain materials to be attracted by magnets, whereas others are not. So if you have a diamagnetic, this means that all electrons are already paired. So when you have these diamagnetic ones, you see that there are no unpaired electrons. What exactly do we mean by paired versus unpaired? Well, that's because this has well, it's two electrons per line, right? So we've only had enough electrons to fill these two. So that means that they have not started overlapping. But if we had more electrons, then you would fill 1, 2, 3, and then you go back 4, 5, 6 to pair them in to backfill. But you don't double them up in the beginning, as we mentioned before. So we can see that we could, in fact, write the electron configurations of all of the elements. Now, it gets really arduous writing out the whole thing. So we also have this idea of writing a shorthand, and that is that, well, if you take a look at the periodic table again, that as we come further down, these are going to all contain the prior information. These here are the noble gases, and they're going to have a complete electron configuration. So what you can do is when you want to write the electron configuration is go back to the prior one in the periodic table and then add the next one on. So in the lower ones, you can't really do that. But these, for example, will take helium, and then it adds on these other additions to helium to get the beryllium, boron, and so on as we work our way down the table. So what does this mean? Well, the further down the periodic table we get, the more complicated it's going to be, because we're going to have more and more electrons, because, well, that's what happens as you go down the periodic table, you grow in more electrons. So that's what this is about. All right, that pretty much covers our first half. Now, the second half, we could talk about the chemical bonding. Next, we're going to talk about the chemical bonding, how the molecular geometry and hybridization of the atomic orbitals comes about. So in the VSEPR model, this is the valence shell electron pair repulsion. And this is going to predict the geometry of the molecule from the electrostatic repulsion between the electron, that is the bonding and non-bonding pairs. So in order to do this, we would start off by doing these steps. First, we'd draw the Lewis dot structure for the molecule, that is putting in the electrons from the valence shells to line those up. Then you would count the electron pairs and arrange them in a way that minimizes the repulsion. That's you're going to put the pairs as far apart as possible. Next, we would determine the positions of the atoms from the way that the electron pairs are shared. That's how the electrons are shared between the central atom and the surrounding atoms. And finally, we would determine the name of the molecular structure from the position of the atoms. So what we might want to do is consider arranging the chloron or the chlorines around beryllium. This is BeCl2. So here we would draw the Lewis dot structure of the chlorines. So chlorine has 2, 4, 6, and 1 electron in each of these bonds. So that's 7. And then beryllium has 2 valence electrons, so it would have a dot in each of these places, which brings this together. So this is what the model would look like. You will have a center and you will have 2 lobes on either side. These are for the chlorines. This gives the maximum distance between the chlorines. So what we're considering here is like what shape would maximize the space of all of these things, and making the linear model is precisely what will do that. This gives you 180 degrees between this, and it results in a linear model. This is what it would look like if we use the beads to construct this. So suppose we want to consider arranging 3 things around the center. So if we had 3 bonds, this would be, for example, boron trifluoride. So here we have a boron, which has 3 valence electrons, and fluorine, which like chlorine also has 7 electrons. So this is in the same group in the periodic table. It's in column 7. In group 7. So this gives us 3 things around. So what these will do is these will lie flat in the plane, and then they will spread out to give the maximum space, which is 120 degrees between them. And we get this shape right here, triangle shape. Now things get a little more interesting when we get to 4 things around the center. And that is because the flat planar geometry no longer is going to be optimal, because you could do it at 90 degrees, but the thing is that you could actually give more space between them if you popped it up and went into the 3-dimensional space. So you think of like what's being shown right here. So you have 90 degrees between the various things right here, but if you could twist these, then it gives you 109.5. This is the tetrahedral angle. And so this gives you the more space. So that's why the square planar is not actually used by molecules, but instead when you have 4 things, it moves to the tetrahedral. Now this is the first instance where actually moving something out of the flat plane is going to give you that advantage. So you get the tetrahedral shape when you're arranging 4 things around the center. So this right here is carbon tetrahydride. So we got 4 hydrogens around 1 chlorine, CH4, just like this. So suppose you have lone pairs now. Okay, and this is why it's important to do the Lewis dot structure, because the lone pairs also are going to have repulsion just like the bonds are going to. So this is why we need to do that. So here we have a nitrogen with a lone pair, right? So nitrogen has 2, 3, 4, 5 things around the center. There are 5 electrons, which you can verify by looking at the periodic table. And so when we have 5 things around, these are going to form these bonds with hydrogen. So we're going to have this lone pair, and then we're going to have 3 things down here. So it makes the tetrahedron shape. But the thing is that the tetrahedron shape is not all taken up by atoms. So it's sort of like the lone pairs are kind of invisible, but not exactly. They're still causing the geometry of the nitrogen. So you would have the hydrogens down here, and although there are only 3 hydrogens, because there's a lone pair, that means there's four things around the center. So it will also take the tetrahedral angles, not the trigonal planar flat one. So this will be the trigonal pyramid molecular shape. So when you trace out the molecular shape, you're tracing out the shape of where the atoms are. When you look at the arrangement of the orbitals, that will take into account the orbitals and the atoms, whereas the atoms version of this for the molecular shape will only just show where the atoms actually are. And so this happens, of course, because we have this lone pair up here, that it takes the same tetrahedral geometry, but the molecular shape looks different because we don't see the lone pair the way we would see an atom. So suppose we have four orbitals with two bonds. Water is an example of this. So here's oxygen. Oxygen has 6 electrons around it, 2, 4, 5, and 6, and hydrogen has 1. So this is bonds between these. So your initial thought might be, oh, water should be linear, but that's actually not true. And the reason is because oxygen is our central atom and in fact has 4 things around it. It has 2 lone pairs, which we can see from drawing the Lewis dot structure. So we have our lone pairs above and below, like so, and then we have the hydrogens. So that's going back in the 2 different positions here. So again, we have those corners of the tetrahedron here in order to make the overall molecular shape. So this means that overall then our molecular shape is not going to be tetrahedral, but it will have the tetrahedral angles. The lone pairs will be invisible, and we will get the characteristic bent water shape. So 3 molecules shapes are going to result from 4 electron pairs around the central atom. So we've seen a number of these different things. So here we have right, you have an A in the center and B going around it. So if B's are all atoms, you will get the tetrahedral shape. But if you have one of these B's being a lone pair, then you won't actually see it. And so the result will be the trigonal pyramid, although the shape of the electronic configuration is exactly the same. And then here is the situation where you have 2 lone pairs and you have 2 atoms, so you'll get the V shape or bent one. So this is like a water, this is your trigonal pyramidal, and this is your tetrahedral shapes. So the bond angle is going to experience a bit of compression due to the lone pairs. In other words, the lone pairs take up a little bit more space than the bond would. Now, it's not perfect, right? So these are all approximate. But what we see is that when we have a perfect tetrahedron, that all of these things are equal, the angle here is going to be 109.5. Now, as you add a lone pair, so basically if you replace a hydrogen with a lone pair, maybe that means the atom has to change, right? Because the electron configuration is different. You would go from 109.5 down to 107, and that means that the lone pair has compressed this a little bit. And now when we have oxygen with the situation of 2 lone pairs, the compression of the bond angle has gone down from 109 all the way to 104.5. So you'll see that you're going to have this compression of the angles as you have more lone pairs. So in other words, the lone pair takes up a little bit more space than just the plain bond. Let's take a look at a tetrahedron ion. So here is a phosphorus with 4 chlorines around it. So 4 chlorine bound, the center atom is most likely to lose the electron to make the ion. So in this case, for example, we have this shape and we have an ion here. And so the phosphorus being in the center is likely to lose its electron. So that the reason why this overall is plus is because, well, why? Because, well, how do you get a plus? It means you have an excess of pluses, or in other words, 1 electron was lost. So did chlorine lose its electrons? No, chlorine did not lose its electrons. It's the phosphorus that lost the electrons. So otherwise, you'd also have to put another, like 1 electron in a lobe out here. These guys are not going to be so happy about that. It's going to get squeezed right out, and that's how you get a plus here, because one electron gets lost from the phosphorus from its valence of 5. All right, so let's consider a situation where the electron does not get lost. So then we're not going to have the ion anymore. So here we're going to have 5 things around the center. What kind of a shape will this make? Well, this is going to make the trigonal bipyramidal shape, right, being shown right here. So you have a trigonal plane that is a triangle planar structure in the middle, and then you have two pyramids, one on the top and one on the bottom. So that's the shape that this will make, right? Being shown right here. So you could have, again, this similar kind of a situation that we had before, where we want to arrange different, we want to arrange the electrons. So we've already seen that the electrons take up a little bit more space than a bond. And so the choices of how to arrange these things would be these combinations shown right here. But if we have these lined up this way, we see that there's a 90 degrees between the electrons, and they're not happy. And if we did it this way, we have a 90 degree here, but if we put them on the plane, then none of these have a 90 degree with another lobe of electrons. The 90 degrees is with the bonds. And since we know that the electrons prefer to have more space than the bonds need, then we would place those along the plane in the center. So you would get the plane in here. And so when you have a situation where you have 3 iodines, it's going to be a linear molecule instead of any of these other possible shapes. So let's take a look at structures of molecules with 5 electron pairs around the central atom. So for example, here is 5 things around. And if all of these are going to be actual atoms, we will get the trigonal bipyramidal, because we have the triangle plane in the middle, and then we have a pyramid on the top and a pyramid on the bottom. Here we have another example, but 1 lone pair. So where does the lone pairs go? Well, we saw that the lone pairs prefer to go in the plane because there's more space. If you're up here, you've got 90 degrees to 3 things. Here, at least 2 of your neighbors are going to be 120 degrees away. So we're going to put that here, and so we're going to get the seesaw shape. So you see how that looks like. A line here and then the little seesaw, because you don't see this. Then we could have the T-shaped molecule. So this will have 2 electron lobes over here, and we'll have these 3 left. So this gives the T shape, which looks like the letter T kind of on its side. And then we also could have 3 electron lobes, and those would all prefer to be on the plane. So they will go like so, and then we'll have the top and the bottom inhabited by the atoms, which we see in this arrangement here. We can also have 6 electrons around the central atom, pushing the limits here. All right, so we could have phosphorus with 6 different things, and we now have an ion in this case, so we have gained an electron. So let's see how this is going to look. So this is going to arrange the lobes on the plane. So we'll have 4 lobes on the plane, and then we'll have these positions above and below, which is going to give us 6 positions. So we're now going to be considering this situation where we have a plane having 4 positions. So this will be the square bipyramidal. So we're going to have a chlorine on top and another chlorine down on the bottom. So these things actually exist. Yeah, they do. All right, so let's consider if we're going to arrange 4 lone pairs to give the maximum amount of space. So if we have this this kind of arrangement where we would put the lobes on the planes, we would get the seesaw shape, because, well, again, very similar to the previous seesaw shape, except the angles are a little different. This would be the seesaw shape. The other alternative would be to put the lobes up above and below, which would lead to the square planar molecule. So we can tell these apart because such a molecule that would be arranged in a square planar is going to result in no dipole moment, because the pull on these various positions is going to be with vectors that are going to cancel each other out, whereas this one would not cancel it out. So here we can see the arrangement of the electron pairs about a central atom is going to follow a pattern, and this pattern is trying to be illustrated to you here. So here we're going to have two things around the center, which is going to result in a linear molecule. Now, if you have three things around the center, you're going to have the trigonal planar situation here. Now, once you move to having four things, you're going to have the tetrahedral structure. And that's going to have the tetrahedral angles. These are like some examples of molecules over here. Here we could have five things around the center, and that will result in the triangle in the plane here, and then something above and below the plane. And then when we get to 6, we have the two poles, and then we have going around this middle here, we have the octahedral center. So we have these names of the structures right here, and these are some examples that we have seen throughout the text. So this here talks about a similar thing, but suppose we have some electron pairs that might include some electrons. So AB2E is A with two B's, two B atoms. This does not mean boron, so we should think of this more generally. And then one electron pair. We're looking at how many things do we have going around the center of this. So this would be an example of this situation. So the trigonal planar is the parent structure, but because we have a lone pair, we would get this to look like the bent. So here we have AB3E. So here is you have four things around the center with one electron pair, so that's going to make the trigonal pyramidal shape, which is being shown right here. This is AB2E2, so this is five things around with two lone pairs. It's going to make this shape right here, so you're going to get the bent from the tetrahedral shape. Now we have AB4E. This is 5 things around the center, so you're going to have the triangle plane in here and the poles above and below. So the place that the electrons would like to go is on the plane, because there's more space, so you'll get this distorted tetrahedron, otherwise known as the seesaw. Here is AB3E2, right? So this has 3, 4, 5 things around the center. So we got these 3, 4, 5, just like so, which gives you the T shape. Here we have AB2E3 to give this shape here. So we're going to have 3 things on the plane, 3 electron pairs on the plane. So this will give us the linear molecule shape. Here we have AB5E, so we got 6 things. This will give us, well, where are the electrons going to go? To one of the poles. So this will give us the square pyramid. And here we have an example of a similar octahedral parent shape, but this is going to have 2 things on the poles, which will give us the square planar shape for the molecule. So the bond moments are going to result from the dipole moments of the molecule, which are going to be the resultant dipole for the shapes being shown. So we see that we can have a resultant dipole going in the up direction, because hydrogen will be pulled towards nitrogen because of the electronegativity, and we also have this lone pair going up. Whereas in this case, we have a dipole going in this direction, and we have dipoles now moving towards the fluorine, which is much more electronegative than nitrogen. So this will result in a dipole moment in the downward direction. Question is, will the molecule have an overall dipole? Well, that has a lot to do with the geometry. This is why this is useful to understand, because you can get a sense of whether the dipole is equal or not. think about those force tables you probably learned about in your elementary physics class. So if all the force vectors cancel each other out, then there will be no net force. This is really quite similar. So here, if you have carbon tetrachloride, you're going to have no dipole moment, although the bonds are really quite polar. Here's another example where the dipole is going to be 0 because even though there is a net force, because oxygen is much more electronegative than carbon, then your dipole moment is also going to be 0. But it's not just about how many things are around the center, because in this case, we're going to have a water, and water has a strong dipole because you're going to have a net force. These are not balanced out by the electron cloud that makes this have the shape that it does. Here's another example down here. So here we have 3 hydrogens and 1 nitrogen. So the net dipole moment is going to be in the positive up direction. Whereas if we have the hydrogens replaced by fluorines, it's going to switch its direction and have a strong dipole moment away from the nitrogen. All right, so I think that is probably a useful place to put things on pause, because the next thing we will need to talk about is the hybridization, that is the mixing of more orbitals, which we will talk about in our coming lectures. All right, so thanks so much, everybody, for joining us, and we will see you next time to continue our discussion of the bonds.